So the goal of this experiment will be for us, of course, to determine the exact concentration of a sodium hydroxide solution. This process, of course, is going to be referred to as standardization. And once, of course, the exact concentration of this solution, of course, is determined, we're going to be using this, of course, in the next experiment to actually, of course, find out exactly what is the acid content, of course, in vitamin C. So please note, the first part of this experiment will involve, of course, preparing a solution of sodium hydroxide. Once that solution is prepared, right, we're going to be, of course, right, the goal will then be to determine its exact concentration. Now you might then say, why do we need to determine, of course, the exact concentration? Because we have just prepared that solution, and we're just saying what? That solution is 0.10 molar. So there's a few things I need for you to note. Sodium hydroxide, of course, is actually referred to, of course, as it's a solid, but it's a solid that is said to be hygroscopic. That means what? That means, of course, that it picks up moisture readily, of course, from the atmosphere. And so even if I weigh out the exact amount of sodium hydroxide, I can assure you that between, of course, right, weighing that sample out and going back to your bench top, that mass will slightly change. In addition to that, sodium hydroxide, when it sits, of course, for a period of time, it's a solid. As the solid, when we purchase it as pellets, it reacts, of course, also with the carbon dioxide in the atmosphere, and we generate, of course, right, you'll oftentimes see that it has, of course, what? A white solid on its surface, and that solid, of course, is what? Sodium carbonate. And so the sodium hydroxide, when it sits for an extended period of time, because of this chemical reaction, please note that that solid that we're going to start off with is actually truly not always very pure. So there's always, of course, a residual amount, of course, of what? Of sodium carbonate, of course, right, on the surface of those pellets. And so we're going to prepare that solution, but once prepared, we're going to then use, of course, a technique or a method known as titration to determine, of course, what? To determine, of course, the exact concentration of our solution. And so we're going to start here with step number 1. So in step number 1, our goal will be to prepare that solution. So how are we going to be doing this? Well, sodium hydroxide is a solid. What do we know? Well, of course, you're given the fact that I need 500 milliliters, and the molarity should be what? 0.10 molar. Well, if my compound is a solid, do you agree? The first step will be for me to determine what? What is the mass, of course, right, of sodium hydroxide that is required? And then once you know the mass of sodium hydroxide that's required, of course, the final step will be to add water. So we're going to be adding water to this solid, right? And please note, we're going to add enough water that until the end, our final volume is 500 milliliters. And so the glassware that we use in the laboratory is referred to, of course, as a volumetric flask. These flasks, of course, measure exactly, believe it or not, to 2 decimal places. And so, if my goal is to obtain, of course, a 500 ml solution of sodium hydroxide, then in the laboratory, of course, I would grab what? A 500 ml volumetric flask. But they come in different sizes. So later in the semester, when you guys are preparing your solutions, you need to make a note that you will need to obtain the correct, right, size or volume, right, for that container. Again, this is known as a volumetric. So just make sure that we're on the same page. It's said to be a volumetric flask. Okay. And so exactly what mass of sodium hydroxide do we need? Well, you're given the volume, of course, and the molarity. So by now, hopefully you should realize what? That there is a relationship between what? Molarity, volume, and moles. Don't forget that in this relationship, volume has to be in liters. And so when you rearrange this equation, we can first calculate what? The moles of sodium hydroxide that is needed. It's going to be the molarity of the solution times that volume. And so the molarity, of course, is what? 0.10, at least that's our goal, right? To make a 0.1 molar solution. So it's 0.10 moles per liter times my volume. Well, that volume is 500 milliliters. And so when I convert that to liters, right? Do we agree? That's going to be what? 0.5, of course, liters. Using your calculators, that's going to give us, of course, what? 0.0500 moles of sodium hydroxide. But that's just the moles of sodium hydroxide, right? That is not the mass. So how do we determine the mass? Well, hopefully, of course, you should recognize that if you know the moles of your compound, using, of course, that molar mass, right, we can determine, of course, the amount in grams. And so per mole of any substance, in this case, of course, it's sodium hydroxide, it has a given mass. Where do I find that information? That is, of course, determined from the periodic table. And so that's approximately 40.0 grams per mole. And so from this calculation, you're going to realize, of course, that I'm going to need what? We will need, of course, in terms of sig phase, this is slightly off, we'll need 2 grams of NaOH. Now, it doesn't matter if I don't weigh out 2 exact grams of NaOH, you should recognize in the laboratory, but whatever mass, of course, that we obtain, right, from that, of course, we will determine the exact molarity. So now that we've prepared our solution of NaOH, sodium hydroxide, the goal, of course, right, is for us to determine what the exact molarity of this solution. And so in order for me to solve for the molarity, what information do we need? Well, I need to know what the moles of sodium hydroxide and, of course, what the volume. So how is this going to be done? Well, this is going to be done, of course, by an experiment, right? A typical acid-base, of course, titration. In this experiment, we're using, of course, KHP. Please note, this is not potassium, hydrogen, and phosphorus. This compound, of course, is referred to as potassium hydrogen phthalate. Its chemical formula is actually, of course, potassium, C8H, of course, 5 and O4. And the molar mass of this compound is 204.22 grams per mole. So please, despite the fact, of course, that I'm using this abbreviation, right, the correct, of course, chemical formula is shown. However, this acid is a solid. And so the acid, whenever an acid reacts, of course, with a base, right, as we said in class, this is going to be our typical neutralization reaction. And in your typical neutralization reaction, what are always our products? Our products, of course, are some salt, right, and water. Now, I'm not including the states here, but when we form, of course, potassium, sodium, and the salt, you should note, of course, that salt is actually water soluble. Okay. So how are we going to be using this, of course, technique to determine, of course, right, the exact molarity of this solution? So prior to, of course, this experiment, we're actually going to first, we're going to weigh out a certain amount of potassium hydrogen phthalate. So I'm using approximately, this is approximately 3 grams of KHP. Now, you should note, if I know the mass, of course, of KHP, which is my acid, can we convert that to moles? Yes. Using, of course, right, this wonderful molar mass, I can therefore determine the moles of my acid. Now, from your knowledge, of course, of chemistry, right, if I have a balanced chemical equation, you should therefore note, if I know the moles, of course, of our acid, do we also know the number of moles, right, of that base? And certainly, this is a one-to-one mole relationship, and so you should note the number of moles of my acid is actually equal to what? The number of moles of my base, which is, of course, sodium hydroxide. And so the only challenge will be, therefore, what? For me to determine the volume, right, of sodium hydroxide. And so the titration experiment, our solid is usually placed in an Erlenmeyer flask. And what I'm going to be doing, of course, I'm going to be dissolving that solid in water. It is extremely important that the solid completely dissolves. Inside the burette, we're going to be adding, of course, our sodium hydroxide solution. Now, care must be taken as I go through this section to make sure that we're recording the volume, right, of sodium hydroxide at the end of this experiment. And I'll explain to you as we do this, of course, in the lab, exactly how we go about using the burette. However, you should note, at the end of this titration, the volume, of course, of sodium hydroxide that was used will be determined. And if you know the volume of sodium hydroxide, along, of course, with the moles of sodium hydroxide, you therefore should be able to report, right, on its molarity. However, these acids, right, KHP when dissolved in water is a clear colorless solution. Likewise, sodium hydroxide is a clear colorless solution. And so in these, of course, neutralization reactions, how will we know when that acid has completely neutralized that base or vice versa? Well, to do so, we use what is said to be what? An indicator. And the indicator that we use in this experiment is phenolphthalein. Phenolphthalein, of course, please note, has a specific color when the solution, of course, is acidic. It also has a specific color when the solution is basic. And so, if I have an acid, and if I add a few drops, of course, of this indicator, I assure you, and you'll see this, that that solution will be colorless. However, if my solution is basic, if we add a few drops of this indicator, then that solution will turn dark pink. So how will we know when we're at that end point / that neutralization point? And so this is going to be a bit challenging as we try to do this, right? So you're at that end point, that neutralization point, when the solution goes from what? From colorless to faint pink. If I add one additional drop of sodium hydroxide, I can assure you that that solution will be fuchsia, right? Very dark pink in color. So manipulating or using, of course, or burette is going to be extremely important in this experiment. But don't forget, of course, that indicators are extremely important, of course, in aiding us, of course, to determine when this, of course, titration is complete. So we're going to be moving on to part 1 of this experiment, where, of course, I'm going to be preparing, of course, our sodium hydroxide solution. And so I laid out, of course, 2.052 grams, of course, of NaOH. I'm going to transfer that to a beaker. And the reason why I'm not placing it directly, of course, in my volumetric flask is that I want to make sure, of course, that that solution, right, that these pellets dissolve completely. So just by using some water, so with the use of H2O, and honestly here you got to remember, it doesn't really matter how much water I add, right? Because we're actually preparing what, 500 milliliters of this solution. One thing you'll notice, of course, with sodium hydroxide is that if I don't mix this, of course, immediately, believe it or not, that these pellets begin to stick to the bottom of that container. I should also point out to you that as I'm mixing the solution, the bottom of this container, right, is actually, fairly warm to that touch, and therefore you should be able to therefore recognize that heat is released in this reaction. And so in chemistry, we refer to these reactions as being, of course, exothermic. And so I'm just going to remove, of course, my cap. Just add enough, of course, water to make sure that I just completely dissolve that sodium hydroxide pellet. Once it's dissolved, I'm going to transfer the solution to our volumetric flask. So I'm just using my stirring rod to make sure that I completely dissolve that sodium hydroxide solid. You'll notice, of course, that the solution that is resulting is actually a clear, colorless solution. And with the aid, of course, of a funnel, I'm going to be transferring the dissolved, of course, NaOH to our volumetric flask. So just as we said before, don't forget we still have, of course, some of the solution, adhering to the walls of my beaker. So the first thing I'm going to do is just to use, of course, maybe another 50 ml of water, to remove, of course, all, of course, the NaOH, of course, from the walls of my container. And And then in the final step, don't forget, of course, our goal here was that we're making, what, 500 mLs, of course, of this solution. I'm just going to keep on adding, of course, water until my final volume is 500 mLs. But please note, this, of course, glassware is calibrated, right? So there is actually, of course, a mark. And so my goal is to get to, of course, the bottom of that meniscus, where it's going to measure exactly, right, 50 mLs. And in the laboratory, right, volumetric flasks come with various sizes. So I can actually have a 10 ml, a 25 ml, or even, of course, a 2-liter volumetric flask. Now, I have to be careful to make sure that I do not add, right, more than the required volume of H2O. And so as I near the end, you're going to notice, of course, I'm going to grab my pipette and then just do this, of course, gradually. Alright, so using my pipette, I want to make sure that I do not go beyond that 500 ml mark. So I'm just going to slowly add, right, the remaining volume, of course, of H2O that is required. Now also keep in mind that I need to make sure that I need to look, of course, right at the bottom of meniscus at the end. Now it's also important to remove the funnel, because don't forget, of course, that, maybe there might be an additional drop or two of water, right, on our funnel. So I think I need possibly another drop. Okay, so I'm going to transfer, of course, 500 mLs of sodium hydroxide to a polyethylene bottle, and I'm going to be storing this for the next 2 weeks, because I'm also going to be using the same solution you're going to see later to actually, of course, determine the acid content of a vitamin C tablet. Perfect. Now I need to make sure, right, that my solution is mixed well. So I'm just going to make sure that the solution is mixed well, and then I'm going to be moving on to the second half of the experiment to determine the exact concentration, right, of my NaOH solution. So with the aid, of course, of a funnel, right, I'm going to be adding, of course, the sodium hydroxide solution to, of course, our burette. I should also point out to you that the burette actually measures backwards. So when it's filled completely, it actually measures, of course, what, 0 mLs. And then, of course, the last graduation, of course, is 50 mLs when we've used, of course, the entire volume of this solution. Noting, of course, into decimal places, this also reads correctly to 2 decimal place. Now, as we add the sodium hydroxide to fill this burette, it's very important, right, that we actually use, of course, a funnel. And I'm a bit short, so please forgive me. But we'll need to make sure that we're using a funnel to avoid spilling. And I'm not quite sure I can do this with my left hand, so here we go. However, it's also important for you to make a few notes. This burette, of course, when it's filled completely, the tip of the burette is also filled, right, and void of any air bubbles. Right now I'm going to open the tip just to make sure, right, it's completely filled and void of any air bubble. So I'm going to return to fill in, of course, the burette. And again, avoiding to go too far over that 0 mark. So we're going to be looking, of course, at the bottom of the meniscus, right, at the end. I'm also going to remove, of course, my funnel, just to make sure that I don't have an additional drop of NaOH entering, of course, our solution. All right. Of course, I will need to adjust this to make sure we're starting off at 0, right? So when it's filled completely, my goal is to make sure that my original value or my initial volume is 0 mLs. So I'm going to be transferring, of course, the solid potassium hydrogen phthalate to the Erlenmeyer flask. And remember, I noted to you earlier, right, that the solid has to be completely dissolved. So I'm going to be dissolving, of course, our acid. And so please note, it doesn't really matter how much water I add, right? That's not going to change the number of moles of KHP in my container. So whether I have 5 moles, of course, of KHP or 10 moles, right? Adding water is not going to change the number of moles. It's honestly just going to change just the concentration of that solution. But the moles of KHP will be the same. And so I added 30 mLs, of course, of water. And now I'm just going to spend a minute or two to make sure that that solid, of course, is completely dissolved. So our solid KHP, of course, is almost completely dissolved. And so I should point out to you that in container number 1, in this flask, what I have here, of course, is 0.302 grams of KHP, potassium hydrogen phthalate. And so you can use that mass, of course, of KHP to determine, of course, the moles. Now, to aid, of course, for the completion of this titration, don't forget I noted that we'll need to use water, a few drops, right, of our indicator. This indicator, so you'll note, when I add the phenolphthalein indicator, it's added to my Erlenmeyer flask with my acidic solution, and I'll need about 2 to 3 drops of the indicator. Notice, of course, that there is what? There's absolutely no color change. So this indicator, of course, is right, results, of course, in no change in color. So it's colorless, of course, in an acidic solution. I'm going to move on, of course, to the next part of my titration by adding, of course, what? My sodium hydroxide solution that we prepared earlier, right, from the burette into our container. Now, as we do this process, there's sometimes actually a few tricks, right, in chemistry. I actually want to make sure that if there's any NaOH, that I wash that, of course, from the walls of my container. So I'm going to be slowly adding, and as I add the sodium hydroxide, realize, of course, I'm also going to be stirring my solution. And initially, you know, I can be a little bit, I don't have to sort of as slowly as possible. But as I near that end point, that neutralization point, I have to be extremely careful. So right now we're adding the sodium hydroxide slowly, not too vigorously. Now you notice, of course, that what? That is, as I'm adding, you should have noted, of course, what a slight change in color. However, that is going to disappear, right, once I mix the solution. Now I think I'm getting closer to that end point. So I'm going to start adding my NaOH, right, well, just about 1 drop at a time. So I'm going to try to control the rate at which I add sodium hydroxide. So hopefully you can see this, that I'm now controlling the rate, but as I add that sodium hydroxide solution, I'm making sure that I'm also, of course, mixing completely. There's oops, and if I go over, I will cry. So that's a little slightly beyond pink, but it's not as bad. I should have also pointed out to you that in the process, I should use my water bottle to remove, right, any NaOH that's actually adhering to the walls of my container. So this faint pink color is actually a tad too pink, but I hopefully you understand exactly the goal. Please note, of course, that the burette reads backwards. So initially we started at 0.00 milliliters, and right now, of course, my volume is at, and I'm just going to use a little bit of paper here to aid me. That volume, of course, is actually 15.0 milliliters. Okay, so in our second titration, please note I'm going to be starting off with 0.328 grams of KHP. And just as before, I'm going to be transferring our solid, right, to our Erlenmeyer flask and dissolving that solid in approximately 30 mLs of H2O. And using, of course, my stirring rod, gold hairs to make sure that that solid, of course, is dissolved completely. Again, right, you should know, of course, that my solution is clear and colorless. So, of course, is my sodium hydroxide solution. And so to make sure that we know exactly when this reaction is complete, we're going to be adding again, right, 2 to 3 drops of our indicator phenolphthalein. Alright, so now that the sodium hydroxide, now of course that my KHP is completely dissolved, I'm going to attempt again, of course, right, to neutralize this acidic solution by slowly adding, right, my sodium hydroxide. And so I know that, okay, my first took about what, 15 mLs. I have a few extra grams, right? My mass here is about 0.02 grams greater. And so, of course, I'm going to hope that I can get down to 13 mLs without this solution, of course, getting neutralized. And as I near about 13 mLs, I'm going to slow things down. You'll notice, however, that that solution, right, where it's hidden, of course, my acidic solution, right, it looks what? Much darker in color, and that's because, of course, we noted earlier that sodium hydroxide, right, in the presence of my indicator, is actually fuchsia, it's dark pink. Okay, so now that I'm for certain I know that I'm close to that end point, I'm going to do my best to just slowly add NaOH. And I will probably know that once I get to about 14 mLs, I'm going to take a minute or two to rinse, of course, the walls of my container. And so with the aid of my wash bottle, not only am I going to rinse the inner walls of my container, but also, of course, right, the tip of my, of course, burette. Now, this will not change, agree, the number of moles, right, of my added, of course, acid or base. My goal now is to do this as slowly as possible and try to avoid going over that wonderful, of course, endpoint. Again, I'm going to rinse that one drop that's hanging onto the tip of my burette. Still not faint pink as yet. So I'm going to see if one additional drop might do this trick. I think I'm almost there, but I'm trying to avoid over titrating this time around. Yay! And so you can know that this solution appears to be slightly just faint pink in color. Oh, just one drop did that. So now you should note, of course, right, how challenging this technique truly is. Okay. Now, if I allow the solution to actually sit for an extended period of time, believe it or not, that this, of course, faint pink color will actually, again, become colorless. And so the challenge, of course, is why. And the reason for that, of course, right, is that the carbon dioxide in the atmosphere will actually, of course, will dissolve in water to form the weak acid, carbonic acid. So if I allow this to sit for some time, I can assure you, of course, that this faint color, pink color, will disappear because I'm going to be regenerating the weak acid, carbonic acid. Now, in terms of volume, the recorded volume here is actually 16.2, about 25 milliliters.